My pleasure to welcome Jim Driscoll, a man who really needs no introduction, but I'll try and do my best anyway. Jim Driscoll is the former president of the Combustion Institute, received a PhD from Princeton University several years ago, fellow of the Combustion Institute, fellow of the AIAA, and his specialty is in understanding the structure and dynamics of turbulent flames in a wide range of conditions. Today is going to talk about some recent work that's been done on high-speed combustion-related or high-speed propulsion-related combustion. So with that, I'll hand over the microphone to you, and I'll just advise the audience, if you have any questions, just put them into the chat or the Q&A in the bottom of the screen here, and we'll list them off at the end of the talk. So with that, I'll turn it over to Jim. Jim?
Isaac, again, thank you for inviting me, and I will try to, I kept the number of slides down so that if I stay within our time limit, we can have some discussion. I also want to thank Wenting and Yiguang for all the work setting this kind of thing up. It's a great idea, great idea. Before I begin, I want to say that this is, I think the key word in what I'm going to talk about is the word relevance. You know, when we hire new people and think about our future in combustion science, the word relevance keeps coming up, and it's a word that's somewhere between applied combustion and fundamental combustion. And so to me, relevance means it's fundamental, but it's relevant to something. And that's what I think the future is leading to. The days of getting a lot of money in really fundamental combustion, at least in the US and perhaps Germany, are gone. And so this is an application. It's been fairly well funded over the years for me, but up and down because hypersonics goes up and down depending on national needs. Anyway, this is work on hypersonic aircraft, and we've been developing what's called a reduced order model that can be used for control of the vehicle. And so a lot of the work I'm doing is related to control, poles and zeros of the transfer functions, and whether the vehicle will stay steady and controlled. And so it's, but the combustion is one important part of a hypersonic aircraft. In fact, it's probably the least understood part of the design of such a vehicle. And AFRL, which is the Air Force Research Lab, is very close to us here in Dayton, Ohio, and we've developed a good relationship with them. And the other person who's helped us out is Kevin Bowcutt. He's at Boeing. He's the designer of the X-51, which had about 4 flights. So many of them were unsuccessful at first, but it was a hypersonic vehicle that Boeing built and tested. And these are some of the grad students who have worked with me. Chris Marley is working now at Boeing on hypersonics, and Chucky is also, and Alex Shoemaker is at AFRL. He's one of the managers there in Dayton. So it's a combined effort. Now, one of the points I want to make, and I hope you can see the screen okay, is we need scaling relations to move into what we call relevant studies of combustion. Now, what's a scaling relation? The example I'm putting up here on the screen is Jackie Chen's DNS simulation of a jet in a crossflow. And then I put underneath it some experiments that we did here at Michigan, again funded by our Air Force, in which we injected ethylene fuel into a crossflow of air that was at 1400 Kelvin. So it's a very difficult experiment to run. You can get auto ignition because you see formaldehyde formed well before any OH, and so there are a whole pathway of chemical reactions taking place when you mix very high temperature air in with fuel. But here's the problem with the combustion community. We all do one experiment or one DNS, and then we sit back and write papers and we generally run out of funding before we can do more. What do people doing relevant research need? They need scaling relations. So what they need is for us to vary all of the governing parameters in a systematic way, and then in some way reduce that to either formulas or simple curves, figures that give us understanding of what all these parameters do. For example, the air velocity coming into Jackie's DNS, the fuel velocity, the density of the air, the density of the fuel, then the temperature of the air is very critical. But we don't have a scaling relation, and we need that to design hypersonic vehicles, because the preferred way of injecting fuel is to inject it out of a port in the wall, so you can cool the wall with the fuel, and you don't have anything sticking out into the high temperature airstream. Now, of course, Ed's with us, and so he's done much work giving us understanding of strain rate using, I would call simple scaling relations, but I think the community could use more. We know the scalar dissipation rate is a way of introducing strain into simulations of turbulent combustion, and yet we only have kind of a vague idea of, you put this in the model and the model gives you some result, but more understanding is needed in terms of scaling relations. Heat release distribution, as I'll show, in a high-speed vehicle, a scramjet-like vehicle, you need to know the heat release as a function of X to determine where is it going to thermally choke and what's the thrust coming out of the engine. Again, you don't see a whole lot of literature in the combustion publications on heat release distribution in the X direction, and how does it depend on the governing parameters. We need more of this information. Another example, before I get into this, is here's a scaling relation I presented at the Princeton summer school when Ed kindly invited me to give a talk there. And this is from the Journal of Fluid Mechanics. It's a real simple idea, but very useful. It's too simple to be, advanced science, but it's very useful for designers. Suppose we have a tube of fuel, gaseous fuel, and coming out at a fuel velocity, and we consider just a cylinder around the fuel. Now, of course, the fuel isn't contained in a cylinder, but let's just imagine that. And then at the edge, there's an entrainment velocity of air that somehow gets rotated around in these vortices and driven radially inward into the fuel. In the Journal of Fluid Mechanics, they've explained this simple idea that you can take the mass per second coming out of the fuel tube, rho u times the area of the fuel tube, and that's the mass per second of fuel going into this cylinder. Now, how much mass per second is there going of air going into the cylinder? Well, we're going to make the assumption that the air comes in at a constant velocity. That's a very crude assumption, an entrainment velocity, and it's going to be u sub e. And you multiply it's rho u a. So rho is the density of the air, u the entrainment velocity radially inward, and this is the area. Pi d is the circumference, and multiplied by the length, we get the area of the curved surface. And we set this equal to the stoichiometric fuel-air ratio, and this tells us roughly the length of mixing required to mix fuel and air to the stoichiometric proportions. And from that, you get simple scaling relations that are, again, in the Journal of Fluid Mechanics, but it simply says that if you make the density of the air larger, you get a shorter mixing distance. Increase the if you if you take the magnitude of the air velocity, this is magnitude here. So if we had a very large air velocity, this term would dominate, and you would be forcing air into the cylinder. Okay, so these are the, I think, useful formulas, because if you're trying to do something relevant, you need to reduce a whole lot of information into simple formulas. And of course, you need to improve these formulas as we go along. So how does this apply to hypersonic vehicles? Let me start out by saying that with a rocket, you can get to hypersonic speeds, but 88% of the propellant that you have to carry along is oxidizer. That's if you're running stoichiometric hydrogen oxygen. So just, we see here that 16 grams of oxygen, and out of the total 18 grams that we carry, that's 88%. So the obvious idea is to, air is free as you're flying along. And even though the density of the air is very low at high altitudes, that's when you reach high Mach numbers. And so you keep the dynamic pressure 1/2 rho u squared constant, you will get a lot of mass flow of air even at very high altitudes until you run out of air altogether. And for this reason, we know that a scramjet burning the fuel supersonically will provide a larger range. And what are the two advantages of a scramjet? Well, you could run a ramjet at high Mach numbers, but what you find is that the inlet shocks are very, very strong to bring the flow to subsonic. And you lose a lot of thrust because of the strong shocks. And also dissociation is a problem, because when you reduce the velocity to subsonic, the static temperature goes way up. The gases will be highly dissociated. And as we know, any dissociated species you put out the back end will cause a loss in thrust. So the scramjet avoids some of that by avoiding shock loss, by reducing shock losses and reducing dissociation losses. However, the penalty is the flame may become too long to fit. So, and this is one of the problems we're having with our simulations now. The smaller vehicles, like the X-51, don't have very long combustors. This is 14 feet long. What is that? About 4 meters long, and that's a pretty small vehicle to burn things, and at Mach 2 in the combustor. Unstart. The X-51 did have an unstart problem. Boeing doesn't like to talk about it, but if you don't have the right heat release distribution in the combustor, then the pressure builds up, and because it's thermally choked in the Ram mode, and this causes higher pressures, and that basically pushes the shock waves upstream out of the inlet. And so you'll have spillage due to a shock wave sitting far in front of the vehicle instead of inside the inlet. And this occurred on the X-51 when they transitioned from gaseous ethylene fuel to JP7 liquid fuel. And what they probably did was not put in the right amount of fuel during the flight. And also, they didn't know how fast the fuel would burn and what the heat release distribution would be, because they simply, actually, they relied on some very crude computer codes that I hate to even talk about, but Boeing was using codes that we would never use in the universities, and especially the combustion part was just totally crude, but they used them anyway. Flameout is also an issue, and heat transfers, there's a lot of funding these days in looking at the heat transfer problems of hypersonic vehicles. And finally, the dynamics people, the control people, are very interested in this problem, because when you go from Ram mode to Scram mode, Ram mode means your subsonic combustion, all of a sudden you thermally choke. I mean, you are thermally choked, and all of a sudden you no longer thermally choke when you go to scram mode. So the downstream boundary condition on the engine very abruptly changes. And so the people doing the dynamics say, well, what do we have to do to keep this aircraft stable when the thrust undergoes a step change, and when the moments on the vehicle change because the pressure distribution changes. So you know, to keep the vehicle trimmed and all the forces and moments balanced during a rapid change from ram to scram is a controls problem. And the people giving us money over the years have been controls people, not so much combustion people. Anyway, to tell you what I'm going to talk about in the next few slides, AFRL people wanted us to develop a what we call a reduced order model, and we call it MASIV, Michigan-AFRL Scramjet in vehicle. The idea would be you would first create a CAD model of a vehicle. And so this is a model of only one geometry with one fuel. And, you know, we have like 4 of these models. So we have actually 2 vehicles and 2 different fuels, but each model is only good for one geometry, one fuel. And you have to add a trim code, because when you think about it, combustion depends on how much fuel and air are going through a combustor, and the vehicle has to be trimmed. So that means all forces and moments have to be balanced such that the angle of attack is known. And the trim code basically chooses 10 different angles of attack and computes all forces and moments and determines when they're all balanced, and that gives us the proper airflow through the engine, and that determines the amount of fuel you have to put in to get the thrust you need. And you don't get to choose how much fuel you put in. It has to be just enough to give you the thrust equal to the drag. Or if you're accelerating, the thrust minus drag has to equal the mass times acceleration. So you don't get to choose this. And if you look at all the literature on these fundamental science projects, very few people worry about, you know, the more relevant aspects, like what determines the amount of thrust you need? What determines the fuel-air ratio? You don't just get to choose it. Complex finite-rate chemistry is absolutely essential. And this is where the work of the combustion community, Iguang and Fokian and the Stanford group. I mean, we just have to know we just have to know something about JP7 fuel, because we have to know how much distance do we need to burn it. Are we going to be putting it out the back end of this vehicle? Okay, and this all has to be done quickly. So how do we do this? Lookup tables. Okay, this is the way of relevant research. You take the jet and cross flow information and you combine it with a turbulent combustion assumed PDF flamelet model, which is maybe the best we can do, but it's not perfect. But then we do all these computations ahead of time and we create tables. They're only good for one geometry, one fuel air mixing geometry, you know, a certain number of fuel injectors, etc. And you put them all in tables, and then then all you have to do is go to these lookup tables and quickly iterate, and you can determine thrust. So this is what we call a reduced order model. It's not a full CFD model, but components are done in CFD and then put into lookup tables. And this is exactly what hypersonic vehicles people want. So the outside of let's say we have a vehicle, the outside we can model with supersonic panel methods. Each panel on the outside is inclined to the flow at a certain angle. And this is all steady state phenomena. We can go to supersonic panel methods ideas and determine the pressures on each panel and give us the lift and drag associated with the panels, okay? That's old technology, and it's pretty accurate. I mean, even if you do full CFD, you're not going to do a whole lot better than a panel method. The shock waves coming into the inlet, we have the method of characteristics, which strictly speaking is best for 2D flow. But if we want to do 3D flow, we just have to run CFD, and we've done that. You know, you run a commercial CFD code, compute the shock wave pattern for a 3-dimensional inlet, but then you have to put it in terms of the forces and moments on the surface for each condition, and the boundary conditions, the exit conditions here that are then fed into the combustion code. So you break this up into components. Now, these shocks are sitting in the right place. You see there's a cowl down here, and there's a shock wave coming out. It comes up near the shoulder of the inlet. And so there will be some more waves produced down here. There's a bow shock that comes in, and here it reflects. So we have to include shock wave interactions, but that's pretty fundamental fluid mechanics if it's 2D. But you have to validate this whole approach, and so you can compare these simulations. Now, getting to the combustor now, how do you model a combustor for a relevant problem? And the answer is you have to pick a geometry. And we picked a jet and a crossflow. And we can add a cavity downstream, but again, that we need equations or formulas that tell us how fast does the fuel and air mix in this geometry. Now, at Stanford, Godfrey Mungall has done beautiful scaling relations of jet and crossflow, but it's for subsonic flow, and we just have to make the assumption that it might apply to supersonic flow. The other thing is that at many labs like AFRL, they've studied this problem and looked at the effect of the cavity on mixing, but even then, they have not come up with a systematic set of scaling relations. This is what you need to put into a vehicle model. Okay, so here's the Mungall Stanford work, and this is really very, very nice. It's in the Journal of Fluid Mechanics. The mixture fraction on the center line of the jet. So now the jet is curved, and it actually has a slope of, it follows a curve x to the 1/3 power, fairly accurately. And then the mixture fraction on the center line depends on the densities and the velocities, and it drops off in the x direction as things get mixed. But Godfrey measured this very nicely for low-speed flow. And then you can assume, again, looking at the experimental data, you can see that the mixture fraction, this is related to the fuel-air ratio, is like a Gaussian function as you go away from the center line of each jet. And then you assume the jets are non-interacting, another crude assumption. And then you make the assumption that many modelers make, and that is that the scalar dissipation rate is proportional to the gradient of the squared of the mixture fraction. So you can determine how Z, related to the fuel-air ratio, varies in the radial direction, and you can come up with a curve fit, basically, for the scalar dissipation rate. And then there is a standard turbulent combustion approach, which is, maybe not the most modern, but it's used in many, many computer simulations, and that is you create a flameout lookup table by solving the counterflow, actually the flamelet equation, which is like the counterflow non-premix flame work. But FLAMEMASTER is the Stanford code that Heinz Pitch developed, and it shows how in this case, the fuel is a function of the mean mixture fraction and the scalar dissipation rate. So this is pretty standard turbulent combustion approach. But then, of course, how do you do the kinetics? We were very pleased to see that Fokyan and USC and the whole group, many of you who are listening are part of this, explains how the HYCHEM reduces fuel to pyrolysis reduces the complex fuel to a number of simpler fuels such as ethylene and methane and other things. And this code is available. We used it. And then, of course, there are many, many reactions in which the simple fuels are oxidized to form water and CO2. And so we ran FLAMEMASTER, the Stanford code, for a flamelet equation. And you obtain results like this. And this is a schematic. You get the mean reaction rate of the fuel as a function of the mixture fraction. And this is sort of centered around the stoichiometric value here. And if you go to higher strain rates, the reaction rate goes down until the flame is extinguished. Okay, and so now you can map this onto the contours from that formula that I just showed, and you get contours of reaction rate. And then we integrate them in the y direction and the z direction. So now we just get we get profiles that are only a function of x, and we can get this should be the reaction rate of the fuel goes up and goes down, and then the fuel is consumed. Okay, but we can get profiles like this for all the species. Okay, now. The problem is, of course, that if you're running a scramjet, you're going to get very large scalar dissipation rates, which is basically telling us that the flames are on the verge of extinction, and you may not burn all the fuel. So if you put this in the engine and you have different pressures, obviously we know that things burn better at 3 atmospheres, and if you're at a high altitude, you may only be getting 1/10 of an atmosphere, and this is a heat release rate result that people need. And then what do you do with this? For this reduced order model, we would put this into the one-dimensional conservation of energy, and you can see the only variable here, the independent variable is x, and the dependent variable is t. But then you have the velocity and the mass flows, and you have conservation equations for momentum and equation of state, et cetera, which I didn't show. But basically, this is just a standard conservation of energy, and of course we don't assume CP constant, so we have to include the enthalpy of formation of every species. But it's pretty standard stuff. Okay. Now the key thing in this whole heat release analysis is what's the heat release rate, and that depends on the chemical reaction rate of each species. And so this is a standard one-dimensional conservation equation for how the mass fraction of each species varies in the x direction, and it primarily is governed by the chemical reaction rate, which comes from the JP7 chemistry. Okay, so you can do all that. Now, this, everything I've said has to be validated or to the best of our ability, and so you get results, but as soon as you get them, you have to ask how good are they, and that's another issue. But you can get these kinds of very interesting results. The Mach number, going through the shock waves, there'll be a series of shock waves, and the inlet method of characteristics will tell us we'll drop the Mach number from 6 through shock waves. But in the scram mode, if we're running an equivalence ratio of 1, which means the mass flow of fuel and mass flow of air are matched, 18-kilometer altitude, that gives us the static pressure and static temperature out here. We see that the Mach number drops down, but it doesn't go to quite below 1. So we're still in the scram mode, and then the gas velocity expands through the nozzle and we get thrust. Static temperature goes way up. This is high Mach number, hypersonic, and as we're bringing the flow from Mach 6 down to a little over Mach 1, and so we're getting a lot of static temperature rise from all of this. First question is, does the flame fit in the combustor? And this is, we have two geometries that we've been looking at, the X-43, which is like an airplane, and the X-51, which is like a drone, which is only 4 meters long. And the answer here is sometimes yes, sometimes no. The X-43 is a bigger vehicle, and yeah, the flame fits in the combustor. If you run hydrogen fuel, it fits very nicely. But if you run the JP7 fuel, sometimes no. And so the fuel is injected, and then it drops down. And this is a good case. In other cases, it doesn't drop down, and you're injecting a lot of fuel out the back end. And our combustion efficiency depends on the water vapor. And so we compare the water vapor mass fraction at the exit to the theoretical value with dissociation. And in some cases like this, you get most of the fuel burned. And again, using the nice HYCHEM chemistry, we can plot the ethylene mass fraction. And, ethylene is formed and then burned. Methane is formed and burned. This is fantastic. The Boeing people love this stuff, and the Air Force, they think this is fantastic. OH, of course, is formed, and the OH recombines in the nozzle. So this is the OH coming out of the combustor, and the static pressure changes. Again, you add heat to a high-speed flow, you drive the Mach number towards 1, which means you drop the Mach number, but you raise the pressure, because static pressure goes opposite of Mach number. And so you get some fairly high pressures as you decelerate the flow. Okay, and then a huge problem is in the ramjet mode, you get thermal choking. And fortunately, there's a lot of good literature and analysis on thermal choking. But unfortunately, from what I see, most people ignore it. I think they don't even know that Shapiro's textbook in 1953 had a beautiful explanation of thermal choking and scaling relations, just looking at the equations. I don't know if so many people have even looked at Shapiro's compressible flow textbook, but this was all done in 1953, and it's really good work. He was an MIT professor. But if you add heat to a subsonic flow, you'll drive the Mach number towards 1, and this is in the Ram mode, so this is all subsonic. And then at some point you get thermal choking. But of course the problem is then you're adding heat after the thermal choking point. So now you're adding heat to what you hope is supersonic flow. So here's this Mach number, and we go supersonic. Now, the heat added to the supersonic flow will drive the Mach number back down to 1. That's not what you want, okay? You're adding heat, drives it to Mach 1, good. Add heat over here, downstream of thermal choking, you will drive the Mach number back down to 1. Not good. Well, but that's why you have the wall of the combustor diverge like this. Because in supersonic flow, if the wall diverges, that will drive the Mach number up. And so you have to have enough wall divergence such that it overcomes the tendency of heat addition to drive the Mach number back down to 1 in this supersonic region. So that's how all scramjet combustors are designed, to have a very simple but important wall divergence to control the Mach number, because we want the Mach number to be supersonic and go out the nozzle in a supersonic manner. Okay, so now now how do you determine where you get thermal choking? Well, in 1953, Shapiro showed, from looking at the equations, that the rate at which the stagnation temperature goes up, which is proportional to heat release rate, when it's exactly equal to this number, which is proportional to the divergence of the wall, where these two curves cross, that's where you get thermal choking. Now, this is this function here, which is this solid line, it depends on the JP7 chemistry, and it's the flame. It's everything we know about combustion. This dA dx is simply a 0, where the combustor is constant area, and then if we just diverge at a single angle like this, then this becomes a constant. dA dx is related to the slope of the wall. So you can design the combustors such that these two are. Now, the problem, of course, is this 1953 analysis had no consideration of the chemistry and the combustion. So what they did was they said, well, somehow the stagnation temperature goes up. Well, you know, in our code and what we can do today, we can nicely compute this, assuming jet and a cross flow and assuming all the things we did, and we get it curved like this. Okay. So this device will work if you properly match the heat release to the wall divergence, and to do the heat release, you need complex finite rate chemistry. And we've published about 9 or 10 journal papers on this, all different components, and we're publishing some more recent work, but it's not in the combustion literature, it's in the aircraft literature. So anyway, what you find is that if you're flying at a certain Mach number, you can fly in scram mode if you don't put much fuel in. Obviously, if you don't put any fuel in, you will have supersonic flow everywhere, but you won't get any thrust. But then as you just put a little bit of fuel in, you'll maintain scram mode. If you put enough fuel in, you thermally choke and you get the ram mode. And then if you put in too much fuel, you unstart. And unstart means that you've created such a large pressure rise that the shock waves in the inlet and the isolator have to be stronger than a normal shock. Okay, so too much fuel, too high of a pressure, the shock waves become too strong, and there is no solution because you can't have the shock wave stronger than a normal shock. And so the only possibility is for the shocks to move upstream and eventually disgorge. And we can predict with our model when that begins, but we cannot predict the dynamics that occur after it begins, and that's an unsteady model. Anyway, to avoid unstart, you need to compute the pressure, you need the finite rate chemistry of JP7 fuel, and you want to also avoid incomplete combustion. And again, this comes from the JP7 excessive heat transfer. We have a paper on that, but I won't talk about that. And we want to avoid flameout again. Okay, so what do the funding people want? Boeing or AFRL in our case? What they want from us is the operability limits. Okay, I'll stop in just a few minutes. They want the operability limits. This is the flight corridor, so this is flight Mach number and altitude. And generally we go along a constant dynamic pressure trajectory. So 1/2 rho u squared is constant, and that's good for lots of things. Keeps the pressures reasonable inside the engine. It keeps the forces on the vehicle, and you stay within this flight corridor. So what are these two solid lines? Can we even estimate what they should be? Well, if you fly too high, eventually the static pressure outside becomes so low that the chemistry stops and you flame out. If you fly too low, obviously your heat transfer is going to be a problem, because the heat transfer depends on the density of the fluid. So if you very low altitude, heat transfer will limit you. The engine will unstart, and that is when the shock waves become too strong. They exceed a normal shock, and that occurs if you're flying too fast at low altitude. And so, I'm sorry, if you're flying too slow at low altitude, if you're to the left of this line, you'll unstart. So you want to start the engine at a condition, you light off the scramjet, dual mode ramjet-scramjet somewhere here, and then you run a ramjet mode, and then at some point it just automatically goes to scram mode. In our code, we always look for a scram solution, and if we can't find it, then it must be a ram solution. And then when we get to this certain point, we can't find a ram solution, and so we have to go with a scram solution. So the code tells you when this occurs based on the fluid equations. Okay, so these are the limits that the Air Force and Boeing want to know about. And these are some computations from one of our Journal of Aircraft papers. It just gives you the numbers. If you're flying at different dynamic pressures, 1/2 rho u squared, you'd be flying up along one of these curves, and so you'd go from you'd light it off around Mach 4.5, and then you would accelerate, and then about Mach 5.2, 5.3, it would transition to scram, and this is what the code will tell you. But also, they want to know, and this is relevance of combustion, what's the minimum fuel needed to ascend? And we know from rocket theory, booster rockets are used to get a very large initial acceleration. And the reason you do that is to minimize the distance you lift the propellant. So if you can get up to the escape velocity of the Earth, within a very short distance, you can then coast out of the Earth's gravitational field. And so you really want to get a maximum acceleration in the beginning, and then coast. But of course, your payload probably has a maximum acceleration limit, especially if there are people on board. And so with this ramjet-scramjet idea, we find the same answer, and that is there's an unstart limit. If you put in too much fuel, you reach this unstart limit. And so you'd like to, the code says you'd like to accelerate as much as possible, but don't go over the unstart limit. And then when you get up to closer to your desired ascent altitude, then you can cut back on the, you keep the acceleration constant, and you get to your final destination. But the nice thing about this type of code is you can do optimization using a method of steepest descent. It's pretty standard stuff, and you can minimize the fuel required, and you get the specific impulse, which is again a quantity that the Air Force wants. And so you accelerate as much as you can, but don't exceed the unstart limit, and then you automatically transition to from ram to scram. In this particular case, it was about Mach 6.8. I'll finish up now, just a few more slides. Stop. Another student, Chris Marley, just put in a fairly straightforward heat transfer submodel, but he did have to include all supersonic formulas, and he also included cryogenic hydrogen fuel as a coolant for the combustor. Okay, and so there's a lot of complicated thermodynamics of liquid hydrogen. But as you might expect, the bottom side of the vehicle is the critical part. And so this is the bottom side, and this is the heat transfer rate. And the leading edge has the biggest problem. And then as you go through each shock wave, you raise the density. And so you get more heat transfer. And then finally, you go into the combustor and very high heat transfer rates, and then out the nozzle, not a problem. And so what he did was he actually did an optimization of this by determining what kind of silicon dioxide insulation, like insulation panels like on the space shuttle, how thick do they have to be to keep your vehicle safe? And it's a fun calculation. It's not combustion, but it's how much mass flow of coolant do you need, and how thick does the insulation have to be? And another concept that NASA has pushed is that any fuel that's not used for propulsion is recirculated back into the fuel tank. Because generally you need more fuel for cooling than you do for propulsion. And so you don't just waste it. If you recirculate the fuel used for cooling back into the fuel tank, but then that limits your flight time, because after about 40 minutes, the fuel is just too hot. It hasn't been used for propulsion. It's used only for cooling, but it's just too hot. Okay, so again, with this combustion submodel and these simple ideas, you can show that you can exceed about Mach 6 to 7 using the thermal protection system that NASA has suggested. And so you either need to protect it better or don't go above Mach 7. It's a problem. So I'll just say that we have improved models of large eddy simulations, of mixing, of flame lengths, of heat release, but each one of these codes is typically only run once. Somebody gets a nice journal paper and they don't give us scaling relations. We have a nice experimental database of fuel air mixing, but again, everybody does an experiment for one condition. We don't have the, a good understanding of what does gas density, gas velocity do, Scalar dissipation rate, yeah, we know it causes strain that puts the flames out, but again, we need to make this a little more relevant. And we don't have any of this information in the supersonic range for JP7, okay? And if we do, the people who have it won't tell us what it is, and even then, it's proprietary or secret. And we need codes that can help us to optimize. And that means we have simple combustion models, but we can then use them to optimize geometries and things like that. And so, I'll finish up by saying there are databases, but they're not very complete. And that's because nobody gets enough funding to run every single parameter. It's very difficult to scale down an engine to fit into a 14-foot long, 4-meter X51 due to the finite rate chemistry of JP7. Okay, we absolutely need finite rate chemistry models. Incredibly, some companies and people building these devices don't include finite rate chemistry. It's just incredible. I don't know how they justify it. We need scaling relations. It's important to match the heat release rate and the wall divergence geometry. Now, the other thing that came out of our research is that how do you control combustion? And you can control the fuel port diameter. So the last thing I'll say is, in a typical jet engine, a turbofan engine, they have many fuel injectors, typically around 30 of them going around in a circle. Some are used only for idle and taxi, and then all of them are used at takeoff, and then only a fraction of them are used at cruise. So the propulsion people know that if you don't want to have too much fuel and you want to vary the heat release, you just inject fuel from certain injectors and then turn the other ones off. Very easy to close a valve. And that's exactly what you need for scramjet. You want big fuel ports or small fuel ports, because the big fuel ports will give you less scalar dissipation rate, less strain. A whole lot of small fuel ports will give you better mixing, but the flame will probably extinguish. Okay, so the idea here is that you probably will need a lot of fuel injector ports, all of different sizes, different flow rates, and they need a control system to put the fuel in the right way. And we need a model to simulate that. So I'll just go back to my, to finish up, I'll go back to my earlier slide. We've done super good work in the community on jet and cross flow experiments, nice strain rate ideas. We need, I think to make this work more relevant, we need to be thinking more about scaling relations. And this last slide I won't go over. It just there's a list of things that we've done and we published in the propulsion literature. Okay, so maybe this will motivate people, and I hope the funding agencies will see that there's a lot of good work can be funded if you just don't focus on one little aspect of the problem and look at the bigger problem.
Great talk, thanks for it. And we've got a number of good questions in the chat box, so I'll just dive right in on them. The first is from Jay Gore. Is the laminar or the turbulent flow speed the relevant quantity?
In our simulation, we are looking at a non-premixed jet in a cross flow, and we are assuming that it's a non-premix flame, and therefore the flame speed doesn't really appear in anything. It's just a it's almost like a fluent or some other commercial code, how they handle a turbulent jet. And now the chemistry is imposed at each fuel air isoline, but the analysis really doesn't have a flame speed. You could question whether this whole approach is as good as using a premixed flame idea, but we didn't use that. We used a non-premixed flame idea.
Okay, we'll move on to the next question from Neil Rodriguez. In terms of scaling relationships for a rich premixed jet and crossflow, I've noticed a lot of the dimensionless numbers for premixed turbulent flames are not used, Karlovitz number, Dom-Kohler number, etc. In the literature, why is this the case? Is it because of mixing after injection? For instance, where would you calculate laminar flame speed at the jet exit or at stoichiometric conditions?
These are excellent questions, and I hope some funding agencies pick up on this, because the simplest approach is just to simply take a mixing approach and look at the, we actually use the mixing experimental relations, and then we impose the chemistry on the isolines. We do get a scalar dissipation rate because we know the gradient of the fuel-air ratio, of the mixture fraction, okay? And so now we're using a formula that is very commonly used by the LES modelers, but how good is it? I don't know. You're taking the mean mixture fraction, the edge of the jet, and you're saying, well, there's a lot of scalar gradient there. There's a lot of strain, a lot of dissipation rate. All of this needs to be assessed and validated and verified. And so the answer is, if I had a lot of money and I was a government person, I would throw it exactly at the question that that was just raised. How do we get all this strain rate information, counterflow flame strain, or possibly premixed flame strain? How do we get that into a mixing formula? And I haven't seen a lot of effort in that regard. I think people are focusing more on the fundamental aspect.
Okay, the next question's from Iguangju. At 1400 Kelvin inlet temperature, the formaldehyde and OH PLIF show it is more like an ignition-assisted flame stabilization than a classical flame stabilization. What's your opinion on the combustion regime?
Yes, it is an auto-ignition assisted flame. Our measurements have shown OH is formed way upstream of the, formaldehyde is formed way upstream of the OH. So that's not the classical picture of either a non-premixed or a premixed flame. Our measurements also show that there's lots of mixing before combustion, and so it's definitely partially premixed, at least. Maybe it's fully premixed, I don't know, but these are all things that we can do. We have the diagnostics. You do, Isaac, and other people do, and it's hard to get a really high temperature stream and to mix. The geometry is important. I don't think you'd ever want to use just a jet injected into a stream. You'd probably put a cavity downstream of it, right? And I think all you DLR people know all about this. All these reduced order models are extremely simple and need to be improved. But what we do is we just show the sponsors what they can do, and they're quite shocked because they think there's CFD people in-house can do all this. And they're using commercial codes, and if you look at what's in some of these commercial codes in terms of combustion, it's hard to believe that.
Yep. Okay, so this brings us to the next question, actually, for myself. The jet and cross-flow scaling relations that you're using, I think, are based on single-phase mixing, gas-gas or liquid-in-liquid. But if you're injecting a liquid fuel like JP7 into a gaseous cross-stream, wouldn't there be a multi-phase physics that have to be considered as well? How would you deal with that?
Yeah, and I've asked Boeing people; they don't know. Now, this JP7 is used as a coolant, and now with the X-51, they just let it burn up and go into the Pacific Ocean, but in a real device, you'd like to use the coolant to cool the walls. The question is, how much of that fuel is liquid form when it's injected? And I don't know the answer to that. If it is liquid or partially liquid, yes, you need a good model of spray formation from a jet in a crossflow.
And that brings us to the next question from George Sidabotham. I hope I'm pronouncing that correctly. It says, as a bit of an outsider, why isn't hydrogen the most obvious fuel for scramjets? It's a gas, no energy to evaporate, simple kinetics, high diffusion, high energy density.
Yeah. Well, when we started this project with the Air Force, our first 4 journal papers were all hydrogen in a really big X-43 like airplane, like a big airplane. Looked like an airplane, had big wings on it and things, and hydrogen works great. It burns fast. The chemistry's pretty simple. We could run the counterflow diffusion flame, FLAMEMASTER with hydrogen, no problem. Everything's good. And of course, the sponsors and Boeing and the Air Force said, no more hydrogen. And the reason is, of course, Boeing's actually looking at this someday in the future as a way of propelling commercial aircraft. Kevin Bowcutt came and gave us a talk and said, someday you'll get up in the morning, drink your coffee, fly to Japan, do your business, and you'll be back sleeping in your bed that night. Now, that's a dream. But if you could fly, let's say just Mach 4, Mach 5 with safe engines, you could do that. And but you wouldn't fly on hydrogen. You would fly on JP fuel because of the safety issue. And the other thing is, as you know, with the space shuttle, if you fuel up the liquid hydrogen, and oxygen is all cryogenic, and even if there's a delay of an hour or two, you have to dump all the fuel and put new fuel in because the pressure will build up in the tanks. So, you've been to the airport, and we've all had 1 or 2 hour delays. You can't do that with cryogenics. You can't. And for drones, let's say you hear there's something bad going on, you want to fly a drone over the Middle East with a camera. You can't just say, well, we'll wait until we pump all the cryogenics in and wait. You want something that takes off immediately. And so for various applications, you need liquid JP fuel.
Sure. Okay, next question is from Peng Zhao. The nature of the governing equations in supersonic and subsonic flows are quite different, i.e. elliptical and hyperbolic, and hence their numerical treatment. How do you deal with the cross-sonic flow in your 1D CFD model?
Yeah, that's a good question. In this 1D model, what we do is we access lookup tables. So for, let's say, the inlet, there's a boundary layer and there are shock waves. We would run a commercial code like CFD++ or possibly Fluent, but more of one of the compressible flow codes, and forget which one they ran, but they'd run a commercial code that's designed for supersonic flow, but it's a commercial code, so it doesn't have all the bells and whistles of a good university simulation. So what you need is to run these supersonic CFD codes. Now with the inlet, the only numbers you want out of there would be the forces in the XYZ direction at one point, which would be the net force that you could put into the trim code. And then you need the exit conditions from the nozzle, which would be the profiles of pressure, temperature, velocity that go into the combustion model, okay? So you don't need all the information about what's in the nozzle, except to determine the forces on the vehicle. And so you can reduce all that CFD to, let's see, three forces, 3 moments, and then profiles at the exit. And, that's a pretty small lookup table after all this. Now, you have to do a CFD for every single case that you are interested in. Then you have to iterate between, and what we use is a proper orthogonal decomposition, which is just a big way of saying Fourier analysis, where you curve fit a bunch of curves and iterate between the known CFD solutions. Okay, so you have to iterate, but you're only trying to get like a handful of numbers out of each component and put it into the vehicle model. So, but each component should be simulated better than what we do. We just this is our attempt.
Okay, next question is, how do we predict heat release profile in a diverging combustor in a diffusive scramjet?
I showed you the energy equation, a one-dimensional energy equation, and it has a term dy I dx. And so if you know the rate at which each species is either going down or going up in the x direction, you can then, now it's one-dimensional, so there's no diffusion in that equation. Okay, it's simply saying everything is, once you know the heat release rate, you're not worrying about y and z directions. Okay, but when you talk about the mixing, you of course have to have these individual jets, and so it's like you focus on the mixing problem and the combustion problem right near the jet, and then you integrate over all those jets, and there may be like 20 jets. And then you get one heat release profile. And yes, we ignore any diffusion. Now, you could write a two-dimensional or three-dimensional conservation equation, and then it would no longer be an ordinary differential equation. But let me just say, Isaac, the people funding us are the controls people. And the controls people want an answer within a few milliseconds on one or two processors. They want to know if something bad happens, what do I do? And they want to know the poles and zeros and the transfer functions of the flight dynamics. They want to know, is this plane going to be unstable or stable? How do I deflect the control surfaces to keep it flying? And they don't want the kind of detail that some of these questions are addressing. They want to know, what do I do when the flames, when the airplane starts to dip and it's not supposed to dip, you know? So they want.
Could be a problem.
And the only way to do that is to create lookup tables and then access them extremely quickly and hope that that works.
Okay, and on that topic, speaking of time scales, I think that's all the time that we have for today's webinar. So we'll close out the question and answer session. My apologies to anybody who whose question I missed. And yeah, if people would just sign on to thank Jim and say goodbye.
Okay, and if anybody has any questions, please send me an email. I'll be happy to answer any questions that I can by email.